Okay, so my name is Darren Ng. I'm from the University of California, Merced, and I'll be presenting our paper on benchmarking object detection models with mummy nuts datasets. So for our problem statement, navel orange worm is a pest that directly attacks almond kernels or mummy nuts. This reduces almond yield and increases reproduction of gnau. Gnau infestation is associated with Aspergillus spp, is aflatoxin, which is a human carcinogen linked to cancer. A loss of more than $1,700 per acre at 20% crop pest damage can be observed in now infested orchards. And sanitation can cost more than $220 per acre, which makes this very costly for almond growers. For this, we proposed the mummy nut object detection benchmark to use a vision system to allow almond growers to more easily monitor gnau disease. Our contribution is our curation of real-world data sets for the task of mummy nut detection. In this, we present two data sets, which are our original and augmented data sets. We design easy-to-use benchmarking tools for our selected models. We present a two-dimensional benchmarking methodology of accuracy and latency. From our observations and results, we provide guidance for different proposed solutions, and our benchmarking data sets invite interdisciplinary research and collaboration. So a few challenges of our data set. Here we have an image from the original data set. And if we take a look at a few of the difficult detections, we can see a few that our models may encounter. In the top left image, we have a camouflaged mummy nut. And the bottom left, we have a low light one, which we lose a lot of surface features of the mummy nut. In the top right, we have a small scale bundle of almond nuts. And the bottom right, we have one behind a very noisy background. And we know that all these contribute to a difficult to detect data set. Further challenges of the data set is the large variety in mummy nuts. In the bottom right image, we have more difficult detection examples that emphasize the large variety in mummy nuts. And in the bottom left, we have a chart that shows distribution of annotation sizes in square pixels. And we can see that we have a lot of varying scale sizes throughout our data sets. For dataset curation, our original dataset is a small dataset of only 33 images. And this is due to the difficulty to obtain data, as data for mummy nuts are only available during a specific season. These are also very large images. So although we have a very small data set, to artificially generate more data, we introduce our augmented data set, which is a larger data set of 294 images and is generated from inputs only from the original data set. And we achieve this by using data augmentations via image transformations, such as rotations and stretching. Each image is centered on an annotation provided by the original data set and is cropped to a size of 200 by 200. And using this method, we can increase a data set by a minimum of 6x. So for our CNN models, we use 4 popular models. You only look once, YOLO, whose detection method is an anchor box, and at a convolutional layer depth of 53 layers. Faster RCNN, which is also an anchor box detector, at a deeper convolutional layer of 101 layers. MobileNet SSD, which is our smallest network, also anchor box, at 28 layers deep. And CenterNet, which is the only model that uses a different detection method of heat map maximum, at a convolutional layer depth of 104 layers. Each one of our selected models help to contribute to tackle a specific difficulty within our data sets. Firstly, noise. Approximately 75% of each image includes noise that hinders visual features. CenterNet is more robust to these feature level noises, and we hope that this model can tackle this issue. Small scale, there's a large amount of tiny objects present within our data sets. And we know that from the previous chart, the smallest with an area of only 121 pixel size. Those CenterNet and faster RCNN are designed to capture objects of all scale sizes. So I hope that these two models can tackle this issue. Large data. As noted before, the original dataset contains very large images of 3024 by 4032. And fast RCN has a very deep network, which in our experiments, we used the ResNet 101 network. And for diversity, given that there's a large variety in the target objects, YOLO performs very well on artwork variations of objects. And we note that this shows high generalizability. And we hope that this can tackle the diversity within our MummyNut datasets. So for the task of annotating and object detection in MummyNuts datasets, we propose a few tools. Our DCA tool is our difficulty class annotation tool, which helps annotators provide an additional flag to each annotation that denotes a specified difficulty class. This difficulty class can later be extracted from detections and be made to further inform what a specific difficulty a model may be struggling on. Our metric eval is our universal metric evaluation for all models in our benchmark. And this is what provides our accuracy results, which we'll show soon. Our data aug tool generates our augmented data set with inputs from our original annotated data set. And the other tools contribute to simplifying the workflow for annotators. So for our CNN model accuracy comparison, here we have our original data set results in the top table and our augmented data set results in the bottom table. And in the first few columns, we have precision recall, average precision values at 0.5 IOU, intersection of union, and the rest are 0.1. So firstly, we note YOLO v3 has the lowest AP score on the original data set, whereas faster RCNN has the highest precision and recall values. We also note that the original data set has large localization precision issues for each model. And we can see this in our AP values from IOU 0.5 going to 0.1. Our values are not stable, and we see a large increase in the numbers. For the augmented data set, YOLO models are more robust to background errors. As we can see, YOLO v3 has the most significant increase in errors from the original dataset to the augmented dataset as 2.6x. And we also see that CenterNet increases background errors from the original to augmented by 29.6x, while MobileNet SSD by 24x. And for the augmented dataset, YOLO v3 and v5 increase recall values by 6.5 and 2.5x respectively. Conversely to other models, precision values also increase. So for the CNN comparison on performance, we first take a look at our original data set and take a look at our latency values here. So YOLO v5 has lower latency than YOLO v3 on the original data set. And we know that this is due to successive versions of YOLO having better optimizations for larger data flow as provided by the original data set. CenterNet has the fastest training time, but the longest inference time. And faster RCNN sees a speedup of 5.85x on A100 over Tesla T4. And this is because of the large network size of ResNet 101 and the A100 having a larger computational bandwidth to accept this larger network size and larger computations. For the comparison on the augmented data set, compared to the original data set, YOLO models now perform equally here. And this is due to the small network or the small input size that's provided by the augmented data set compared to the original data set. MobileNet SSD performs much faster here on the augmented data set. Again, this is due to the small input size of the augmented data set and the small network size of MobileNet SSD appreciating this small input. Faster RCNN, again, sees a speed up of 5.68x on A100 over Tesla T4. And we note this for the same reason that we observed in the original dataset of a large computational bandwidth for faster RCNN. So for the conclusion of our results, our accuracy results, our augmented dataset improves model recall value by an average of 2.77x. And YOLO models see the best increase in both precision and recall values. To this, we note that YOLO would perform very well on our augmented dataset as compared to the original dataset. For performance, faster RCNN has the most significant speedup from Tesla T4 to A100, and this by 5.76x over both datasets. And YOLO models have the fastest overall inference speed over all datasets. And this concludes my presentation. Thank you for listening. Are there any questions?